Okay, well, welcome back to our course on software engineering, and we're making some good progress here. So we're going to be continuing on in our system dependability and security section. And so the material that we're going to be focusing on today, we'll be looking at security engineering. And so the topics that we'll focus on are the security and dependability, security and organization, security requirements, security system design, and security testing and assurance. So in general, security engineering, this consists of the tools, techniques, and methods to support the development and maintenance of systems that can resist malicious attacks that are intended to damage the computer-based system or its data. It's a subfield of the broader field of computer security. So we're getting into the whole cybersecurity area. So a couple of dimensions, you have confidentiality, integrity, and availability. For confidentiality, the information in a system may be disclosed or made accessible to people, programs that are not authorized. And so that's what you want to prevent. And integrity, you want the information in a system may be damaged or corrupted. So you want to prevent that and ensure the integrity is there, and make sure that for availability, that access to the system or its data is normally available, and making sure that always occurs. So in terms of security levels, there's a couple things. There's the things at the infrastructure security level, the application security level, and the operational security level. For infrastructural security, this is concerned with maintaining the security of all the systems and networks that provide an infrastructure and a set of shared services to an organization. Application security is concerned with the security of individual application systems or related groups of systems. And finally, operational security is concerned with the secure operation and use of the organization systems. So here's an illustration of the layers where security may be compromised, and so can go all the way from the application down to the network and computer hardware. That can be hardware things that could be compromised. You could have things in the operating system, general applications, something in the browser, email, etc., database, middleware, and reusable components and libraries, etc. So basically, just about anything can be involved in that. So in terms of application and infrastructure security, the application security is a software engineering problem where the system is designed to resist attacks. Infrastructure security is a systems management problem where the infrastructure is configured to resist attacks. And the focus of this chapter is the application of security rather than the infrastructure security. So for system security management, there's the user and permission management. This deals with adding and removing users from the system and setting up appropriate permissions for users. For software deployment and maintenance, this is dealing with installing application software and middleware and configuring these systems so that the vulnerabilities are avoided. And finally, attack monitoring, detection, and recovery. This is monitoring the system for unauthorized access, to design strategies for resisting attacks, and developing backups and recovery strategies. For operational security, this is primarily a human social issue. It's concerned with ensuring that people do not take actions that may compromise system security. So you don't tell others, you don't leave computers logged on, things like that. Users sometimes take insecure actions to make it easier for them to do their jobs, and so that needs to be monitored and mitigated, and there is a trade-off between system security and system effectiveness. For security and dependability, the security of a system is a system property that reflects a system's ability to protect itself from accidental or deliberate external attack. Security is essential as most systems are networked, so the external access to a system through the internet is possible. And security is essential prerequisite for availability, reliability, and safety. For fundamental security, if a system is a network system and is insecure, then statements about its reliability and its safety are unreliable. These statements depend on the executing system and the development being used the same. However, intrusion can change the executing system and or its data. Therefore, the reliability and safety assurance is no longer valid. So here's just some terms that we'll be talking about, and you can refer back to this, think about the asset, what you're trying to protect, the attack, control, exposure, threat, and vulnerability. And so we'll be getting into this as we go through this. So here is like, specifically if we think of the MentCare system and what would be the asset, this would be the records. The exposure is a potential financial loss from future patients that seek to go and they go otherwhere. The vulnerability, say a weak password. What is a weak link in the system? An attack is a impersonation of an authorized user. A threat is an authorized user will gain access, and finally control is a password checking. And so those gives you some ideas of how they could be trying to deal with these things with the MentCare system. In terms of threat types, there's the inception threat that allows an attacker to gain access to an asset. A possible threat to the MentCare system might be a situation where an attack gains access to the records of an individual patient. Interruption threats will allow an attacker to make part of the system unavailable. Possible threat might be denial of service attacks on a system database server so that the database connections become impossible. You could have a modification threat that allow attacker to tamper with a system. So in a MentCare system, a modification threat would be where an attacker alters or destroys patients' records. And then for fabrication of threat, this would allow an attacker to insert false information into a system. This may not be something that would be an issue for MentCare. For security assurance, you can have vulnerability avoidance, attack and detection elimination, and exposure limitation and recovery. For vulnerability avoidance, the system is designed so that the vulnerabilities do not occur. For example, if there is no external network connecting, then external attack is impossible. For attack detection and elimination, the system is designed so that the attacks on vulnerabilities are detected and neutralized before they result in an exposure. For example, virus checks find and remove viruses before they affect a system. For exposure limitations and recovery, the system is designed so the adverse consequences of the successful attack are minimized. For example, a backup policy allows damaged information to be restored. For security and dependability, security and reliability would be the first part. If a system is attacked and the system or its data are corrupted as a consequence of that attack, then this may induce system failures that compromise the reliability of the system. For security and availability, a common attack on a web-based system is a denial of service attack where a web service is flooded with service requests from a range of different sources. The aim of this is to make the system unavailable. Security and safety, this would be an attack that corrupts the systems or its data means that the assumptions about safety may not hold. For security and resilience, resilience is a system characteristic that reflects its ability to resist and recover from damaging events. So those are some things to think about. Okay, for security and organizations. So security is a business issue. Security is expensive. It is important that security decisions are made in a cost-effective way. There's no point in spending more than the value of an asset to keep the asset secure. Organizations use a risk-based approach to support security decisions and should have a defined security policy based on security risk analysis. Security risk analysis is a business rather than a technical process. For organizational security policies should set out general information access strategies that should apply across the organization. The point of security policies is to inform everyone in an organization about security. So these should not be a long and detailed technical document. From a security engineering perspective, the security policy defines in broad terms as the security goals of the organization. The security engineering process is concerned with implementing these goals. Security policies, the asset that this is concerned with the assets that must be protected. It is not cost effective to apply stringent security procedures to all organizational assets. Many assets are not confidential and may be made freely available. The level of protection that's required for different systems of an asset needs to be thought about. For sensitive personal information, a high level of security is required. For other information, the consequences of loss may be minor, so a lower level of security is adequate. The responsibility of individual users, managers, and the organization. The security policy should set out what is expected of various users, say strong passwords, logging out of the computer, office security, etc. And with existing security procedures and technologies that should be maintained, for reasons of practicality and cost, it may be essential to continue to use existing approaches to security, even when these have known limitations. So for security risk assessment and management, risk assessment and management is concerned with assessing the possible loss that might ensue from attacks on the system and balancing these losses against the cost of security procedures that may reduce these losses. Risk management should be driven by an organizational security policy, and risk management involves preliminary risk assessment, life cycle risk assessment, and operational risk assessment. For preliminary risk assessment, the aim of this initial risk assessment is to identify generic risks that are applicable to the system and decide if an adequate level of security can be achieved at a reasonable cost. The risk assessment should focus on the identification analysis of high risk levels to the system. The outcome of a risk assessment process are used to help identify security requirements. For design risk assessments, this risk assessment takes place during the system development lifecycle and is informed by the technical system design and implementation decisions. The result of the assessment may lead to changes to the security requirements and the addition of new requirements. Known and potential vulnerabilities are identified, and the knowledge is used to inform decision makers about the system functionality and how it will be implemented, tested, and deployed. For operational risk assessment, this risk assessment process focuses on the use of the system and the possible risks that can arise from human behavior. Operational risk assessment should continue after a system has been installed to take account of how the system is used. Organizational changes may mean that the system is used in different ways from those originally planned, and these changes lead to new security requirements that have to be implemented as the system evolves. Okay, let's talk about security requirements. So for security specifications, this has something in common with safety requirements in both cases you are concerned and the avoidance of bad things happening. And there are a couple major differences. The safety problems are accidental. When safety failures occur, you can look to the root cause and that led to the failure, and shutting down a system can avoid a safety-related failure. And then finally, safety-related events are not generated from an intelligent adversary. So here are types of security requirements: identification requirements, authentication requirements, authorization, immunity, integrity, intrusion detection, non-repudiation, privacy, security auditing, and system maintenance. So these are all the kind of things that would be involved in this area. So for security requirement classification, there's risk avoidance requirements that set out the risks that should be avoided by designing the system so these risks simply cannot arise. Risk detection requirements define mechanisms that identify the risks as if it arises and neutralizes the risk before losses occur. And risk mitigation requirements set out how the system should be designed so that it will recover and restore system assets from some loss that has occurred. So here's how a preliminary risk assessment process for security requirements could look. And so you start with the asset identification, you assess the value, you look at the threat identification. And so with the threat value, then you do an exposure assessment. And for this other piece, you do a threat identification, look at the attack potential and possible ways, how you can be controlling the identification, the feasibility assessment. And so as a result, the attack assessment, the feasibility assessment, and the exposure assessment then defines the rationale for the security requirement definition that you would use. So these charts just walk through that. And so you have the asset identification, the asset value assessment, the exposure, and the threat identification. And so we just talked about these on the last chart. So we'll just skip over that. And ultimately, what this is trying to do is come up with the security requirement definition that you define a system's security requirement, and these can be infrastructure or application system requirements that are based upon what you found by going through the information in this diagram. So what about the Metcare system? We could be doing an asset analysis in a preliminary risk assessment report for this. And so you're looking at the information system, the patient database, and individual patient record. And so you determine the value and the exposure for each of these three main components. Then you look at what is the threat and control analysis that would be part of here. So you consider a threat, say an authorized user gains access, its probability is low. And the way you can mitigate that and control it is only allow system management from specific locations that are physically secure. And this would be a low cost of implementation, but care must be taken with key distribution to ensure that keys are not available in the event of an emergency. And then for an authorized user gains access on the system user and access confidential information. So this would be a high probability. So this is something that you're going to be focusing on more. So it requires all users to authenticate, and all changes to patient information needs to be tracked. So security requirements for the Metcare system: the patient information has to be downloaded at the start of a clinic session to a secure area. All patient information in the system should be encrypted. Patient information shall be uploaded to the database after a client session, and a log on separate computers from the database server must be maintained if all changes made to the system database. So some good practices there. What about misuse cases? Misuse cases are instances of threats to a system. There can be an interception threat. The attackers gain access to an asset. Interruption threats. Attackers make part of the system unavailable. Modification, that an adversary tries to tamper with things, and a fabrication threat. False information is added to the system. So here's an example of what that might look like. And so an attacker is trying to get access and looking for vulnerable ways that they can get into the transaction or viewing information of patients. So in terms of the transfer, here is just playing this out, that the actors would be, say, like a medical transcription receptionist or a patient with a patient record system. So a receptionist may transfer the data, and the data is this actual information treatment summary. You have the stimulus would be what the receptionist would be doing, and the response would be confirmation from the patient record system. And so for the receptionist to do this, she must have the correct security permissions to be able to access the patient records and the patient record system. So here's what an interception might look like. And so you have an attacker that has managed to get into this. And so the attacker is involved or having some awareness of those that information. And these are the kind of things that you would want to be looking at. Say, like an attacker might be trying to spoof a server, or the network is modified in some way so that the packets can be visible to an attacker and be decoded. So how do you mitigate this? So all network equipment must be maintained in a locked room. So you limit the access. You have certificate-based client-server communications, and all systems between the client and the server must use secure socket layer and HTTPS protocols as an example. So what about secure systems design? And so security should be designed into a system. It's very difficult to make an insecure system secure after it has been designed or implemented. So this gets into the architectural design. How do architectural design decisions affect the security of a system? And with good practices, what is accepted good practice when designing a secure system. In terms of design compromises, this is dealing with adding security features to a system to enhance the security affects other attributes of the system. So it gets into performance and usability. Adding security checks slow down a system so its response time or throughput may be affected. And in terms of usability, security measures may require users to remember information, require additional interaction to complete a transaction. This makes the system less usable and can frustrate system users. In terms of design risk assessment while the system is being developed and after the system has been deployed. So those are some things that could happen at different points in the development and deployment. More system information is available, and as this occurs, the system platform, middleware, and the system architecture and data organization, vulnerabilities that arise from design choices may therefore be identified. So keeping in mind of risk assessment during the development phase can be helpful. And so here's what the design and risk assessment could look like. And so you have your system requirements and you're starting to formulate your system design. And so you have your technology choices, architectural design, and design assets, and all these are fed into a risk assessment and design some requirements that they might postulate that, you know, if you do some minor modifications during the design phase, you can make it a lot less risky. For protection requirements may be generated when knowledge of information representation and with knowledge of information representation and system distribution. Separate patient and treatment information limits the amount of information that needs to be protected, and maintaining copies of records on a local client protects against denial of service attacks on the server, but these may need to be encrypted. So here's looking at the design risk analysis. And so you have the design assets and you're trying to do an assessment. And so this, we had this figure before that you can see how this flow, but we're trying to now think in terms of the design and risk requirement changes that would be important to minimize risk. So what about the use of commercial off-the-shelf components? System users, authentication using a name and password combination, that would be good. You could be looking for that. The system architecture is a client server with clients accessing the system through a standard web browser. So if you can have the browser secured, say HTTPS and other types of encryptions, and information is presented in an editable web form. So here are some vulnerabilities associated with technology choices. So you can be thinking in terms of password authentication, so you don't want to have passwords that can easily be guessed, and you don't want to have unauthorized reveals of passwords for client server architecture using web browsers. So you want to ensure that the server is not subject to denial of attack service, but there's a confidential information. You want to make sure it's not any confidential information is not left in the browser cache. And you want to make sure that the browsing security loopholes don't exist that might lead to unauthorized access. You want to ensure that the use in terms of editable web forms, you want to have fine-grained logging of changes is impossible, and authorization can't be varied according to a user's role. So for security requirements, password checkers shall be made available and shall be run daily. Weak passwords shall be reported to the system administrators. Access to the system shall only be allowed by approved client computers, and all client computers shall have a single approved web browser installed by the system administrators. For architectural design, 2 fundamental issues have to be considered when designing an architecture for security, that is protection and distribution. How should the system be organized so that critical assets can be protected against external attacks? And for distributions, how should system assets be distributed so the effects of a successful task are minimized? So these end up being possibly conflicting. If assets are distributed, then there are more expenses to protect. If assets are protected, their usability and performance requirements may be compromised. So for protection, so you can be thinking of a couple layers, a platform layer, application level, and then a record level. For platform level, you're thinking about the top level controls on the platform on which the system runs. For the application, you're thinking about specific protection mechanisms built in the application itself, say like additional password protection. And for record level, this is protection that is invoked when access to a specific information is requested. These lead to a layered protection architecture. So here is an example of those three layers and the kind of things that would be involved for each. You have authentication, authorization, and file integrity management for platform. For application, you're looking at having a database of logins, ensuring the database that authorization for users is existent, that you have transaction management and data recovery in case issues come up. And then finally, for the record level, you have the record of access authorization, you have record encryption, and record integrity management. And all this is controlling the patient records, which is your crown jewel, if you will, of what you have with the Medcare system or some other medical type of system, if you're considering that. For distribution, distributing assets means that attacks on one system do not necessarily lead to complete loss of a system service. Each platform has separate protection features and may be different from other platforms, so they do not share a common vulnerability. Distribution is particularly important if the risk of denial of a service attack is high. So here's a picture of a distribution assets in the equity trading system. And so you can be seeing how this might work. And so say you have these different offices in New York, in London, and Frankfurt, and Hong Kong. And so there's some tailored type of things that are specific, the currency and other types of things that would be localized that you would then have that more focused for each node. In terms of design guidelines for secure engineering, design guidelines encapsulate good practices in secure system design. System guidelines serve two purposes. They raise awareness of security issues, and they can be used as a basis of a review checklist that is applied during the system validation process. Design guidelines are applicable during software specification and design. So in terms of design guidelines for secure system engineering, here is a handful of them. And so you can just be mindful of all of these things, base security decisions on an explicit security policy, avoiding a single point of failure, trying to have fail security, balancing between security and usability, having user log actions, user redundancy and diversity to reduce risk, specify the format of all system inputs. You want to have compartmentalization of your assets. You want to design for deployment and design for recoverability. So this is just more details for each of those guidelines. And so I'm going to just quickly go over these. So for explicit security policy, you want to define security policy for the organization that sets out the fundamental security requirements. You want to avoid single points of failure. So you ensure that a security failure can only result when there is more than one failure in the security process. For fail securely, when systems fail for whatever reason, you want to ensure that the sensitive information cannot be accessed by unauthorized users. For balanced security and usability, you want to try to avoid security procedures that make the system difficult to use. So this may be getting into the design in various ways. So for user logging, you want to maintain a log of user actions to be analyzed and discovered for who did what. And so there's a paper trail, if you will, and you want to use redundancy and diversity. So this keeps multiple copies of data and use diverse infrastructure so the infrastructure vulnerability cannot be a single point of failure. For specifying the format of all systems, if the input formats are known, then you can check that all inputs are within range. For compartmentalization, the organization of the system of the assets are in separate areas, and users only have access to the information they need. You want to design for deployment so that there's minimal deployment problems, and for recoverability design so the system it has an ability for easy recoverability after an unfortunate successful attack. Okay, what about secure system programming? So here are some aspects of secure system programming. Vulnerabilities are often language specific. Array bounds checked in is automatic in languages like Java, so that's a good thing. However, millions of programs are written in C and C++, and so you need to be careful of things that are written in those languages. Security vulnerabilities are closely related to program reliability. And so programs without array bound checks can crash. So actions taken to improve program reliability can improve system security. And so here are just a handful of guidelines. Limit information, check all inputs for validity, provide a number of exception handlers, minimize the use of error-prone constructs. You want to have the reset capabilities, check array bounds, include timeouts for external components, and enable constants that represent real-world values. We've had this list before, so maybe just be mindful of that. In terms of security testing and assurance, for security testing, this is gets into testing the extent to which a system can protect itself from external attacks. Problems with security testing can happen is that the security requirements are shall not requirements. And so they specify what should not happen, and it is not usually possible to find security requirements and simple constraints that can be checked. And the people attacking the systems are intelligent and look for vulnerabilities. They can experiment to discover weaknesses and loopholes in the system. For security validation, there is experience-based testing, penetration testing, tool-based analysis, and formal verification. And these are all the techniques that can be used to help validate the security. So for experience-based testing, the system is reviewed and analyzed against the types of attacks that are known to the validation team. For penetration team, you can have a red team. A team is established whose goal is to breach the system and simulating the attack. You can have tool-based analysis where various security tools such as password checkers are used. And then you can have formal verification where the system is verified against a formal security specification. So I won't get into this, but here's examples of entries in the security list that you can be thinking about. And then just to finish up, a few key points. Security engineering is concerned with how to develop systems that can resist malicious attacks. Security threats can be threats to confidentiality, integrity, or availability of a system or its data. And security risk management is concerned with assessing possible losses from attacks and deriving security requirements to minimize losses. To specify security requirements, you should identify the assets that are to be protected and identify how security techniques and technology should be used to protect these assets. Key issues when designing a secure system architecture include organize a system structure to protect key assets and distributing the system assets to minimize the loss from such an attack. Security design guidelines sensitize system designers to security issues that may not have been considered. They provide a basis for creating security review checklists. And then finally, security validation is difficult because security requirements state what should not happen in a system rather than what should. Furthermore, system attackers are intelligent and may have more time to probe for weaknesses than is available for security testing. Okay, well, that's it for this lecture. Thank you very much.